Hi, I am Shanaz. In last lecture, we introduced the notion of a fundamental group. So we were discussing. So we set this notation for. So this pi one of x naught. This is the set of all up to homotopy classes, such that this f is a path. F is a loop at base point x naught. At base point x naught. So this x naught is in the space x. So if we consider this set up to the homotopy, then we claim it that this set here, this is a group with respect to the operation. If we take two elements in this set, then this is the binary operation here, which is defined to be the homotopy class f dot g. So with respect to this operation, this is the group. So we are going to prove that this is a group with respect to this binary operation here. So this is the proposition. This set pi 1 x naught. This is a group with respect to the product, with respect to the product if we take two classes here, two elements here, then this product is defined to be the product f dot g. This product as binary operation. So first of all, we are going to prove that this operation is well defined. So we have this operation here, f dot g is class of f dot g. So we need to prove that this operation here, this is well defined. That is, we have to prove if f prime is homotopic to f and g prime is homotopic to g, then this product here, this is also equal to this class here. So that is what we have to prove in order to prove this product is binary. So let us prove this. So first of all, we show that the group operation on pi 1 x naught is well defined. This is well defined. One can note here that this is definitely a binary operation. So now it remains to prove that this is a well defined binary operation. So for this, let us suppose that f is homotopic to f prime and g is homotopic to g prime, or where the homotopies say why the homotopy is f1 and f2. So if f1 is the homotopy such that, so these two maps here, these two maps here are homotopy where this homotopy, and these two maps here, they are homotopy where this homotopy. So this means that is f1 say s0, this is this little f, and f of s1, this is this little f prime. Similarly, so this is f1 here, and f2 s0 is this little g here, and f2 s1 is this little g prime here. Now since these f and g are loops, so and these f big f1 and big f2, they are homotopies. Therefore this f1 0s is same as f1 1s is same as f2 0s, sorry 0tt. Let us make this variable t here. So this is t here, so this is t here, this is t, this is t, and this is same as f2 1t. So these are all equal to x naught, because we are dealing with loops with fixed base point x naught. So that means here for this square, so this is I cross I, and this is the homotopy f1 here. So here we have two loops here, say this is f and this is f prime. Now this input here, this is mapped to this line here, this loop here, and this input here, this is mapped to this line here. Now these are the pointers 0 1, sorry, so the points on this line, they are the pointers s1, and these are the pointers s0. Now these input here and this input here, these are mapped to this point, because so the point is 0t and 1t, they are mapped to point x naught where this homotopy f1. So these points are mapped to x naught for all t in I. That means this line here and this line segment here, this is mapped to, and this point, say this is point x naught. Similarly, same is the case with f2. Similarly, if this is a square here, so this is I cross I, this is the homotopy f2. Suppose this is our space here, and let us suppose this is g and this is g prime, g and g prime. So this line segment is mapped to g, and this line here is mapped to g prime. Now these two vertical line segments, they are mapped to point x naught here. So this is the same space here, x and x. So this is all happening in x. Now what we need to prove, we need to cook up another homotopy. So let f from I cross I to R, so sorry, x is defined as, now this I is the closed unit interval. So this is given as f of st, it is actually called, so this is f1 of 2st when this t lies between 0 and half, and it is f2 of 2s minus 1t, where this t is in another half, sorry. So note that f1 and f2 be continuous, so f is continuous. Also f of s0, that is same as f1 of 2s, sorry, f1 of 2s0 and f2 of 2s minus 1 and 0. This t is between 0 and half, sorry, this s here, so this is s here. So this is again s here. And this is also s here. This is one here. Now this is same as, now this is same as, because s is in s lies between 0 and half, that means 2s lies between 0 and 1. So f1 of say, let us substitute 2s is equal to say x, so f1 of x0 is this f here, and in the other half it is g here, because when we restrict f2 to 0, so f2 to 0 is g here. Similarly f of s1 is f prime g prime, sorry, yes, of course, f prime g prime. This means that this further implies that now f being continuous, so it serves as a homotopy between these two maps. Hence f is a homotopy between f dot g and f prime dot g prime. So if these two maps are equal, their homotopy classes are also equal. Therefore homotopy class of f dot g is same as homotopy class of f prime dot g prime. But this operation, but definition of this binary operation, this is same as f prime dot g prime. So hence we are done, because we proved this thing here. So this implies that this binary operation here, this is a well defined operation. Now it remains to prove the other group axioms. So let us prove another group axioms. So we are looking for all those loops which are based at point x naught. So to prove the identity, so identity action, note that we have proved that if, so in previous lecture in previous lectures we have proved that, so note that if f from say the interval I to x, so if this is a path with endpoint is say x and y, then we proved that constant path cx product with f, this is homotopic to f, and this f is homotopic to f product with the constant path cy. But here this x and y, they are both equal to x naught. Here x is equal to y is equal to x naught, because we are dealing with loops. So this means that this cx naught f is homotopic to f is homotopic to f dot cx naught. So this constant loop cx naught, this serves as an identity of this set pi 1 x x naught. Therefore this constant loop cx naught, which is same as the class, because this class contains only this element here, so this is equal. So this is in this x x naught. So one can observe that and one can observe that this, if we take this homotopic class and product to this class with this cx naught, this is same as the homotopic class of f, which is same as the homotopic class cx naught, and it is product with f. So this means that this homotopic class of cx naught, this will serve as the identity element of pi 1 x x naught. Hence cx naught will serve as the identity element of this set here. Next we prove the inverse of elements, inverse action. So this is the action of existence of inverses of elements. So also we have proved earlier that we have proved earlier that if f from I to x, if this is a path with endpoints x and y, then f product with its inverse, this is same as the constant path cx and f inverse product with f. This is homotopic here, and this is homotopic to the constant path cui. So this implies that therefore if f is a loop with base point x naught, then we have f product with it is inverse, that is this constant loop which is homotopic to this thing, and this constant loop is again homotopic to f product with it is f inverse product with f, or the product here f product with f inverse, this is the constant homotopic class of constant loop cx naught, which is equal to the homotopic class of f inverse with f. So this means this f inverse is the inverse of f in x, hence the homotopic class of f inverse. So this element here, this is the inverse of f in this set here. Now it remains to prove the associativity. Now for this associativity we again have proved earlier that, so we know if f, g and h, they are the paths in the space x with such that the endpoint of f is the initial point of g and the endpoint of g is the initial point of h. Then if we first travel this path, this product path fg, and then travel h, this path is homotopic to if we travel first the path f and then the this product to g and h. So these two are homotopic. But here f, g and h, they are the loops with base point x. But if f, g and h are loops with base point say x naught, then so then these classes, then we have the homotopic class of, then obviously these classes F, G and H, they are the elements of uh, they belong to this set here. So now let us prove the associativity. So we know that this product here, this is homotopic, this is the same equivalence class of this path here, because these maps are homotopic. So this implies equivalence class of f g dot equivalence class of h is same as equivalence class of f dot equivalence class of g and h. So this is by definition of this binary operation here. So this further implies that this f and g composition with product with this class here, this is the class f, then take it as product with g and h. So this proves that this proves the associativity. Hence this set here, this is a group. Now this group is called the fundamental group of the topological space X with a base point x not in X. So let us make this definition here. So this is the definition here. The group by one of x naught is called the fundamental group of the fundamental group of the topological space X with a base point x naught.